Okay, we're going to carry on with looking at really the first part of the thermal physics unit. We split this into two sections because it was running a little long. So our earlier section looked at atoms as a philosophical idea, looked at the evidence for atoms, and don't forget this is evidence for atoms in the days before we were able to actually see atoms. Using modern technology, using modern scanning and tunneling electron microscopes, we can actually see atoms. But that's only a recent development. We were still confident that atoms existed 100 or so years ago. Okay, and it was Einstein's explanation of Brownian motion that really explained atoms. We also, in the first part of this video, looked at the energy that substances have, internal energy, because of their atoms and molecules. They either have kinetic energy, or they both have, kinetic energy, which is where the atoms or molecules are moving around or rotating or vibrating. And they have potential energy, which is formed from the bonds between atoms and molecules, either internally, which is kind of chemistry and is released during chemical reactions, or the bonds between molecules overall, which gives you solids, liquids, and gases. No bonds in gases, which, by the way, means no internal energy, if you forget about the chemistry part for gases, but there is internal energy in solids and liquids. And that internal energy, that internal potential energy, is changed when the substance changes state from gas to liquid to solid, solid to liquid, liquid to gas. Today, in this section, I just want to look at a little bit more of a modern model for the atom. Here is a modern model. Now, this is not the current best picture of an atom by any means. This is definitely a non-quantum atom. But you will be looking at modern models of atoms later. This is all we really need to look at the moment. Excuse me. In the middle, you have a nucleus. The nucleus includes protons and neutrons, and on the outside you have electrons. As you may have seen in an earlier unit, the ratio here is all wrong. This is not a two-scale diagram. In reality, atoms, the size of an atom overall is 10,000 times the size of a nucleus. If the nucleus was the size of a football, or a tennis ball even, at the middle of a football field, then the atoms, the electrons would be flitting around in the stands, the size of flies. So most of what an atom is actually empty space. Now we needed to know that very basic definition of an atom and introduction to the structure of an atom to introduce this word isotopes. All these three atoms that you see described in front of you are carbon. They're all carbon because they all have 6 protons, and it is the number of protons which determines an element. However, they do have slightly different number of neutrons. What that means is that they're slightly different weights or have slightly different masses. These 3 different isotopes of carbon are known as carbon-12 because it has 12 nucleons, 13 because it has 13 nucleons, and 14 because it has 14 nucleons. Carbon-12, carbon-13, carbon-14. Right. Keep that in mind. Let me now introduce you to the unified atomic mass unit. Atoms are very small, 10 to the minus 25, 26, 27 kilograms. And it doesn't make a lot of sense to be using kilograms as a unit to describe atoms or parts of atoms. Instead, we make use of the fact that protons and neutrons are pretty much the same weight or the same mass. And we use this to define sort of an average. So one atomic mass unit is 1/12 of the mass of a carbon-12 atom. So a carbon-12 atom has 12 nucleons. Divide the mass of that, the electrons have a very small mass indeed, divide the mass of that by 12 and you will get 1 U. So one relative unified atomic mass unit, which is equivalent to 1.66053891 times 10 to the minus 27 kilograms. So it's just a unit of mass with that number of kilograms. If you want to measure the mass of an isotope, as we said, you measure it in unified atomic mass units. By definition, the mass of one carbon-12 atom is 12U. The mass of a hydrogen atom is 1. The mass of an oxygen atom is 32 or 16. Get that right. If you want to take the mass of a molecule, you have to just add the atomic masses of the constituents. So for water, which is H2O, you take the 16U and plus 1 for each for hydrogens to give you 18U. Much simpler than doing it in kilograms. And it has another advantage. To talk about that advantage, let me introduce you to the mole. Not the furry burrowing creature. And if you want to give yourself a nightmare, Google star-nosed mole. But no, mole as in an amount of substance. It's defined as the amount of a substance of a system which contains as many elementary entities as there are atoms in 0.012 kilograms of carbon-12. And its symbol is MOL, mol, which is just kind of lazy. Why not just add an E? And 1 mole, which is a number, it's an amount, equals the Avogadro constant. Now that's a really poor explanation. Basically, it's quite easy. If you have 12 grams of carbon-12, you have that number, Na, of atoms. If you have 1 gram of hydrogen-1, you have that number of atoms. If you have 16 grams of oxygen, you have that number of atoms. Okay, because oxygen is 16. 1 mole, by the way, Avogadro's constant is 6.022 times 10 to the 23. So every time I've said a mole, you just need to know that that is a number. It's this number, 6.022 times 10 to the 23. So to repeat myself, molar mass, the mass of 1 mole of a substance in grams equals U. So 1 mole of carbon-12 has a mass of 12 grams. 1 mole of I think helium has a mass of 4 grams. And the number of moles, basically changing that equation around, the number of moles present in a sample is given by the mass divided by the molecular mass. So previously we said that the molecular mass of water was 18, so twice 18 is 36. So if you had 36 grams of water, you'll have 2 moles of water molecules. Pretty easy. Now, one little twist, because of the isotopes I mentioned earlier, if you're dealing with real carbon, then the atomic mass of carbon is not actually 12, it's 12.011, because as well as the carbon-12, there's some carbon-13 and carbon-14. So you have to take that into account, but that's not normally too difficult. A good periodic table or data booklet or the internet will give you the actual relative atomic mass of the element. And similarly, the molecular mass works the same. Say carbon dioxide this time, carbon-12 generally, oxygen 16, 2 16s is 32 plus 12 equals 44. But the relative molecular mass is actually 44.01 grams per mole because of the isotopes of carbon and oxygen. Okay, so we've now looked at the development of the idea of atoms. We looked at evidence for atoms, the modern model of atoms and energy, and how to count atoms. All that information about protons and neutrons, we don't really need to know it very much. We need to know it in this topic, really, so that we can use molar calculations properly. And in order to explain these 12.011 values of U, I needed to look into isotopes, so I thought we'd go through a little bit into a common model of the atom. It should really be revision from grade 9 and 10, and obviously we will be going to a lot more detail in a future unit. For now, for the rest of this unit, we can pretty much forget about whether we're talking about atoms or molecules or whatever, and just refer to particles and particle theory. This topic is a very 18th, 19th century unit, and back then they didn't know about atoms, molecules, and subatomic particles like we do. We don't really need that information for this unit. Okay, thank you very much.